Okay, so let's get to some examples. Uh, let's say that x is equal to 3y to the fourth plus 2y squared. And I want to find not dx dy, but for some reason I want to find dy dx. So this is a function. Y is being my independent variable. X is dependent on y. But now I want to flip it around and say, okay, I don't know what the inverse of this function is directly. I don't think you can find one, but I can find it indirectly using my differential rule, because dx is equal to the differential of 3y to the fourth plus 2y squared. And passing through and doing my power rule a couple times, this is equal to 12y cubed dy plus 4y dy. So dx dy is equal to 12y cubed plus 4y, which tells me that dy dx is just the reciprocal of that. 1 over 12y cubed plus 4y. And that's as good as I get, because I can't replace y with x. I don't know what its relationship is, but that's fine. Dy dx, y is a function of x, and so this is a perfectly good solution. Another example would be x is equal to, let's say, y plus 2 root y. And just like in the last problem, I want to know what not dx dy is, but what dy dx is. So just like in the previous problem, I find the differential of x first, use that, and we'll use our inverse rule. So this is the differential of y plus 2 root y. Should have written it this way, differential of y plus 2y to the 1/2, because now I can deal with rational powers. And this gets passed through. That's just differential of y. And again, here, this follows by our power rule. The exponent will come down, become our new coefficient. So I'll be multiplying it by 2, which is 1. And I subtract 1. So this is equal to dy plus y to the negative 1/2 dy. So that means dx dy is equal to 1 plus y to the minus 1/2. But that's not what I wanted to know. I want to know what is dy dx, but that's simply taking the reciprocal. So dy dx is 1 over 1 plus y to the minus 1/2. In this next problem, I'm not going to necessarily be doing reciprocals, but I want to take just an opportunity to give an example of a rational power. So if y is equal to x to the 5/3 minus x, and let's just raise it all to the negative 2 power, and we want to know what is dy dx equal to. So computing the differential of y, this is the differential of x to the 5/3 minus x, all raised to the minus 2 power. So first things first, we're going to deal with exponents. So the exponent comes first. It's going to come down, become my new coefficient, and it subtracts 1 to get my new power. So this is equal to negative 2 x to the 5/3 minus x, all raised to the minus third power, times the differential of our u. So that's x to the 5/3 minus x. Now, working this differential, we're going to come through, and of course it's going to distribute across the subtraction. And I'm going to do 2 steps in 1, because when I take the differential of this, even though it's a rational number, it's still the same rule. It comes down, it'll become my coefficient, and I'll subtract 1, right? So this is equal to negative 2 times x to the 5/3 minus x raised to the negative 3 power, all times, okay, the differential here is 5/3 x to the 2/3 dx minus dx. So now that I've got differential of y, it's this whole mess. I've got my dx's, I'm done. And so dy dx, I simply divide through by dx, which will cancel these two dx's. So I get that dy dx is equal to negative 2 x to the 5/3 minus x to the negative 3 times 5/3 x to the 2/3 minus 1. And that's our answer. And in this final example, I want to show how we can find the equation for the tangent line to the inverse of a function. So we've got the equation y equals 3x cubed plus 7x, which we could graph and look at it. But I want the equation of the tangent line to the inverse of this function, right? Not to y equals 3x cubed plus 7x, but if I had its inverse, if I knew what it looked like, what would that look like when x equals 1? So, right, so I can more clearly write this out. If I said f of, so y equals f of x is our 3x cubed plus 7x, then x would be our f inverse of y. So now y is our independent variable, where x is our dependent variable. And we know that, well, before we go any further, let's kind of investigate what we know about this. Well, if x is 1, y equals f of 1, which putting 1 for x just gives me 10. That means that 1 is equal to f inverse of 10. Right? So I want to know what is the equation of the tangent line over here for this function at the point when y is 10 and x is 1. And this is key about inverses. You've got to keep this straight, that we flipped the dependent and independent variables. So this is now, the first coordinate corresponds to my independent variable, and my second coordinate corresponds to my dependent variable. And so then the equation of my tangent line will be x minus 1 is equal to the derivative of x with respect to y, evaluated when y is equal to 10, times y minus 10, right? That's the standard form of our tangent line. So all we need to do is figure out what dx dy is. So I'm going to kind of squirrel this over to the side and work this out. Well, again, I don't know what f inverse is directly, but I can use my inverse theorem. So dy is equal to the differential of 3x cubed plus 7x, which is equal to, this power rule comes down, that becomes a 9, so this is 9, and the exponent decreases by 1, so that's a 2 dx, plus, and then the differential comes right over here, passes through the constant, dx. So dy dx is simply 9x squared plus 7, telling us by the inverse rule that dx dy is 1 over 9x squared plus 7. So then dx dy when y is 10, well, we've kind of got a problem. Because in my equation, I don't have any y's, right? And that happens quite often with inverses. I only have x values. But I know when y equals 10, back here, by relationship, when y is 10, x is 1. So derivative of x with respect to y when y equals 10 is the same as the derivative of x with respect to y when x is 1, which is equal to 1 over 16. So now I know what that is, and so finally the equation of my tangent line will be x minus 1 is equal to 1 over 16 times y minus 10.